Hello, and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be talking to you about the operational amplifier voltage follower, or the operational amplifier voltage buffer. And essentially, it's a negative feedback loop, as shown here, this line here. It's a closed loop. It uses the non-inverting it uses the non-inverting op-amp configuration. And there are a couple of things that we want to notice about the ideal op-amp, right? And again, if you don't remember this, you can check out my op-amp video posted in the timestamp above. But essentially, for an ideal op-amp, we know that IP is equals to IN, and that VP is equals to VN, where P is positive and N is negative. And essentially, we want to first define this follower or buffer. And we say that the voltage follower or the voltage buffer is a unity gain. So this means that AV is equals to 1. A unity gain device that isolates the input source from variation in the load resistance or load impedance, RL. And so to better understand this, we want to essentially look at a circuit, okay? We want to look at a circuit that has a VS, so a voltage input or voltage of the source, an RS, and an RL, which is also called the voltage divider circuit. So this is the voltage divider. And we've studied this in the past, where VO is equals to RL, or this resistor, divided by RL plus RS times VS. And as you can see, VO is dependent on RL and RS, all right, both in the numerator and the denominator. And sometimes for certain applications, we don't want this to be the case. And this is where the buffer comes in. So what I'm going to do is I'm going to redraw the buffer. I'm going to say the voltage buffer. And essentially what it looks like on the inside, again, we talk about this in the op-amp video, is this an input resistance, R input of infinity. It's a voltage controlled op-amp. So it has an RO of 0 or very close to 0. Again, this is very close to infinity. So large input resistance and a very small output resistance. And we collect a V out. And this is the source resistance. And this is the source's voltage. And we loop this system back over to the V out. And we can also connect an R load here. And this R load could be a motor, it could be a speaker, or anything like that. And don't forget, your op-amp always has power rails. So plus 10 volts, minus VCC, minus 10 volts. Again, this is where it gets the amplification from, right? So just to recap here, if this is around 0.1 millivolts, the highest this can be, let's say this is plus or minus 0.1 millivolts. The highest this can be is plus or minus 10. It's 1 millivolt, right? So just basically this times 10. But don't want to sidetrack too much here. But we say that, okay, the current going in here, let's call this, so this is the positive terminal, this is the negative terminal. P is extremely close to 0 because, again, this resistance is extremely big. So it's acting like an open circuit. So no current is going to want to flow through there. And the current coming out, IN, is extremely close to 0. So that's where we get IP is essentially IN, which is equals to 0. And so then now the voltage here, let's call this voltage, VP. All right. Since there's no current flowing through here, as a result of that, Vn is equals to Vp. If you can't see that, basically consider the voltage drop across this resistor. This resistor V is equals to Ri times Ip. But since Rp is equals to 0, the voltage across this resistor, there's no voltage drop, is 0. So the voltage that's here has to be the same voltage that's here. And since this is just a wire, that means that the voltage drop at VO is also Vn. And again, here is IP equals to 0. So that means there's no voltage drop here. This is 0 volts. So what we can conclude and we can say is that VO is equals to Vn is equals to Vp is equals to Vs. Or we can say then that Vs or VO is equals to Vs. And we know that AV, the gain of this circuit, is VO over Vs, which is equals to 1. So this is where the unity gain comes from. Again, remember, this means that this is not acting like an amplifier, right? It's just mapping Vs over to VO. It's not so it's not amplifying the signal. It's not doing anything. This was a situation here, in a situation where we were trying to amplify it, or just trying to show you how an amplifier works. But in this situation, we're just mapping Vs to V out. If you have any questions on this, please leave them down in the comment section below, and I'll be sure to get back to you. So what I'd like to do now is I'd like to define the actual definition of an op-amp buffer. So op-amp buffer. And it's pretty straightforward. It says that the output of the voltage buffer or follower basically follows, this is important, the input voltage signal or source while remaining immune to the changes in RL or R load, because it has a high input resistance and a low output resistance. And here, this it here, immune to the changes in RL because it, we're talking about the op amp in this situation, right? So the op amp has a high input resistance and a low output resistance. So we like that characteristic for the buffer, okay? And that's why it acts like a buffer, because of these characteristics, all right? So now let's go ahead and do an example here. So let's go ahead and do an example. And let's consider the following. Let's consider the previous example we did with the voltage divider. So let's do the voltage divider. And let's consider that, again, we have this V source we have this RL, RS, VO, VS. And we consider that VO is equals to RL over RL plus RS times VS. And what I'm going to do is I'm going to make a table. I'm going to consider a table where RS is in kilo ohms. Okay. RL is also in kilo ohms. We're going to calculate V in volts. We're going to calculate the percent change, right? In percent, obviously. And then we're going to see if we require a buffer or not. All right. So the first one we're going to take is when RS is 1K and RL is 0.1K or 100 ohms. So again, this is RS is considered to be greater than RL. We get 0.1 over 0.1 plus 1, which is around 0.09. And to calculate the change, we take 100 minus 0.09 over 1 times 100. This gives you around 91%. So you're right. This is, again, given that VS is 1 volt. All right. So V out changes by a whole 91%. So if you give me 1 volt and RS is 1K and RL is 0.1K, my voltage output is going to be 0.09, which is really, really low, right? We're almost getting no gain at all, right? We're losing all our signal basically. So in this situation, we would consider that, yes, you do need a buffer. So the next situation is, imagine if RS is 1, RL is 1. So, they're equal to each other. So this would be 1 over 1 plus 1, which would be 0.5. And then the percent change would be 100 minus 0.5 over 1 times 100. This gives you around 50%. So you're still losing half your signal. So if you could guess correctly, you would say you would still need a buffer. So let's go into situations where RL is greater than RS. So this is 10. So then this becomes 10 over 10 plus 1. This is around 0.91. And if you do 100 minus 0.91 divided by 1 times 100, you would get around 9%. And, depending on what your project is, you would probably use a buffer here. It just depends on whether or not what you're doing. So then let's increase this even more and say that RS is 1, which is a lot greater than, let's say, 100K. So again, you would get 100 over 100 plus 1. This gives you 0.99. This is 100 minus 0.99 over 1 times 100, which is around 1%. And again, there's no signal loss here, so you probably wouldn't use a buffer. So there's a few concepts we want to learn from this, okay? And I'm going to start with these two. All right. And essentially, what you notice here is that RL is less than or equals to RS, correct? And what I'm going to do is I'm going to rewrite that and make RS to be extremely big. So I'm going to make RS to be almost like an open circuit and make RL to even just be a closed circuit. So this is VS and this is VO. As you can see, VO, if RS is equals to 1, VO is equals to 0. So 100% of my VS is lost, right? It doesn't map to VO. Okay, so that's where we get a term like this, or maybe like this, in a little bit less of an extreme case. This is called loading. We call this We call this loading, and then I guess I'll formally define it as when you need to drive a low impedance without loading the source. And this loading term essentially comes from how much current is drawn from the source. And essentially, another way to look at it, just to reiterate, is let me put some real values here. Let me say this is 10 meg, and this is just 1 ohm. As you can imagine, when Vs pushes current through this loop, a very small amount of current, almost negligible, is going to drop here, and all the current is going to come to this load here. Okay, so that's where the loading comes from. All my current is gonna be dumped on here. As a result, this VO is gonna be pulled to basically 0 volts. Or another way you look at it is VO is equals to RL, which is 1 over 1 plus basically 10 meg is basically infinity compared to 1. Times Vs, and 1 over infinity is basically 0. So there's a lot of ways to look at this loading effect, but this is what it means by loading the source. So I hope that makes sense. If you have any questions, please let me know down in the comment section below. And the second case is a situation where RS is less than or very small compared to RL. And this is the ideal case. We want this case. So consider that I have. So since RS is very small, we can just consider the wire, and this is our open circuit RL. And obviously, you can see here that RS just maps to RL. Oh, sorry. You can see here that VS just maps to VL, and RL doesn't really impact the schematic. So there's many ways to look at it, and to see when you need a buffer. And in this case of loading, so let me go back to the loading situation. If I had an extremely big resistor RS and I passed it through a buffer, the voltage here will be mapped here. This is AV is equals to 1, and this is V out. And it doesn't matter what my load is. So VS. So I hope this makes sense. Again, if you have any questions, please leave them down in the comment section below. Another quick example of when you would use a buffer is, and again, this is a little bit more on a higher level analog analysis course. But if you had a amplifier, right, this is your V in and this is your V out. Your V out, or your AV gain, or your V out over V in, this is RD, this is VDD, is going to be GM times RD. All right, and this is a pretty high gain. All right, just this is a pretty high gain. Now, if you were to attach something like a speaker here, which is around 8 ohms, this would be in parallel with 8 ohms, and it would drop this gain. So this gain would drop down. So a way engineers go around doing this is they say, okay, let me keep my gain of my amplifier, V out over V in is equals to GM RD. And let's say V in is equals to 1 volt, and this is VDD, this is RD. And again, so then the voltage out here, V out, is, let's just say 1 times 10, so 10 volts. What we're going to do is we're going to attach a buffer. Okay? So then, before attaching our speaker, 8 ohms. So essentially, this amplifier is not affected, right? I'm still amplifying the signal to 10 volts, and I'm putting in this buffer here, and 10 volts is 10 volts is located here, V out 2 as equals to 10 volts, because it's just a buffer, right? But then it's not affecting this amplifier. So if you want to explain this in word, you could say when you want to isolate a sensitive or high impedance voltage source from a load that would otherwise affect it. All right, so again, this load here is affecting this high impedance, right? Because R in here is very, very high. It's affecting it, so as a result, we would use a buffer. If you have any questions, please leave them down in the comment section below, and I'll be sure to get back to you. Please like the video, share the video. Check out my YouTube channel, and also share and like my videos on my YouTube channel. Thank you. Have a wonderful day. Bye.